Welcome to Chromatography-Mass Spectrometry. So mass spectrometry is often paired with chromatography to separate components of a sample and then provide qualitative and quantitative information about those components. Mass spectrometry requires high vacuum to prevent ambient gas molecules from colliding with the ions during the ion separation, but gas chromatography is a high-pressure technique. And thus, most of the material exiting the chromatography column must be discarded, and this is helped by using a capillary column for the chromatography, as smaller volumes of eluent will exit the column, and the pumping system of the mass spectrometer then removes most of the eluent before the ion separation occurs. The capillary column can be directly connected to the mass spectrometer inlet using a heated transfer line. We can also pair liquid chromatography with mass spectrometry, but the liquid creates a huge volume of gas upon vaporization, and most of the gas must be removed before ion separation can occur. And furthermore, non-volatile solutes, as in phosphate buffer, must be avoided or they will clog the injection port. The two most common methods for ionizing the eluent from liquid chromatography are electrospray ionization and atmospheric pressure chemical ionization. In electrospray ionization, also called ion spray, the liquid from the chromatography column enters the steel nebulizer capillary, so that's coming in here. And note that a coaxial flow of nebulizing nitrogen gas also enters via that same capillary. For mass spectrometry of cations, then the nebulizer is kept at ground and the spray chamber is kept at minus 3500 volts. And the resulting electric field at the outlet of the nebulizer combined with the flow of nitrogen gas to create an aerosol of charged particles in the spray chamber then. And usually the ions that vaporize from the aerosol droplets existed in solution in the chromatography column. For example, protonated base, like BH+, and deprotonated acid, A-, can be observed. However, analyte M, whether neutral or charged, can complex with other stable ions in solution to form other ions. For example, we can get the protonated MH+, where the mass then is equal to the mass of M plus 1. We can get other masses like mass plus 18, mass plus 23, mass plus 39, mass plus 45, mass plus 59. And note that there's little fragmentation of the ions in this case. Cations from the aerosol are then attracted towards a glass capillary held at minus 4500 volts, and gas flowing from the atmospheric pressure over here in the spray chamber carries the ions through that glass capillary into the next chamber over here, in which a vacuum pump keeps the pressure at around 2 torr. So let's examine the ionization process in greater detail. The large voltage between the steel nebulizer capillary and the inlet to the mass spectrometer causes redox reactions to occur, such as iron solid being converted into iron 2+, and 2 electrons come out. We have H2O liquid, so water, gets converted into oxygen gas and hydrogen ions plus some electrons. These electrons then flow through the external circuit, and this creates an excess of positive charge in our liquid here. And the charged liquid that exits our capillary then forms a cone here, called a Taylor cone, then a very thin filament there, and then it breaks up into a spray of tiny droplets over here. The droplets shrink to around 1 micron in size through solvent evaporation, at which point the repulsive force of the excess positive charge equals the cohesive force of surface tension, and then the droplets continue to lose mass by ejecting very tiny, roughly 10 nanometer sized droplets, and these tiny droplets then evaporate and the ions are now in the gas phase. So note that it's possible for the analyte to react with species such as the hydroxyl radical, so care must be taken in interpreting the mass spectrum. However, the spectra tend to be much simpler to interpret than in electron ionization due to the lack of fragmentation in the electrospray ionization process. So the lack of fragmentation in electrospray ionization helps to identify our molecular ion, but it doesn't give us much structural information. And thus, sometimes it's useful to intentionally increase the fragmentation. This can be accomplished via collisionally activated dissociation in the region between the glass capillary and the skimmer cone here. The skimmer cone is that bit there. So the gas in this region is mostly nitrogen at around 2 torr. And if we keep the metal layer coating the glass capillary outlet at plus 40 volts and the skimmer cone at minus 20 volts, then the potential difference is about 60 volts. And cations leaving the glass capillary are accelerated through this potential difference of around 60 volts, which provides enough energy to cause fragmentation upon subsequent collision with our nitrogen molecules. And decreasing this potential difference then decreases the fragmentation. So we can control the degree of fragmentation by altering that skimmer cone voltage. So in atmospheric pressure chemical ionization, heat and a coaxial flow of N2 convert eluent into a fine mist from which the solvent and analyte will evaporate. As in the chemical ionization in the ion source of a mass spectrometer, then atmospheric pressure chemical ionization creates new ions via gas phase reactions between the ions and molecules. A high voltage applied to a needle in the path of the aerosol creates an electric corona, and this corona is a plasma containing charged particles and transfers electrons to the aerosol, thereby creating ions in the aerosol. For example, MH+ can be formed via a sequence of reactions shown here. If we have a nitrogen molecule, an electron may stimulate the emission of a second electron that then gives us a radical with a +1 charge. That can then react, and we go through a series of reactions, and we eventually end up with a proton surrounded by a number of water molecules that then reacts with our analyte M. That gives us our protonated M species and some number of water molecules back. Now, analyte M may also capture an electron to form an anion. So the M plus an electron gives us the M-, and again, note that this is going to be a radical because most neutral species have an even number of electrons, and thus by capturing one electron, M- now has an odd number of electrons. So an analyte molecule XY might also capture an electron and then dissociate, so XY plus an electron might give us our radical X and our Y- anion. An anion could also deprotonate a weakly acidic analyte AH, so we could have AH react with Y- to give us A- and HY. An analyte M must usually be capable of protonating to form MH+ in order to be observed, because if it doesn't protonate, then it may not form any ions at all, and if it doesn't form any ions, then we can't detect it in mass spectrometry. So atmospheric pressure chemical ionization generally creates ions with a single charge and is not suitable for macromolecules like proteins. So we can increase the selectivity of mass spectrometry for individual analytes and decrease the response to everything else, thus decreasing the background noise, using selected ion monitoring and extracted ion monitoring. So let's examine the liquid chromatogram of a mixture of herbicides that are labeled 1 through 6, spiked at around 1 part per billion into river water. Using ultraviolet absorbance detection, the chromatogram is quite congested. It looks something like this. And so you can see we've got labels 1 through 6 over here, but those are tiny peaks on top of this broad background. So the simplest way to use the mass spectrometer as a detector is to add the current of all ions of masses greater than a selected value, and this is called a reconstructed total ion chromatogram. And this still gives us a fairly congested spectrum. Again, you can see now we've got a lower background compared to our peaks 1 through 6, but we still have a bunch of other stuff in there. But we could set our mass spectrometer to monitor just a small number of mass to charge values instead of all of them. And this is called selected ion monitoring. A selected ion chromatogram for which only mass to charge of 312 was monitored is shown here. So you see we've got this very, very low baseline with very little noise, and then we've got peak 6, and then very little else. And so you can see that we've got our 6th herbicide here is coming out, and almost nothing else is generating a signal at that mass to charge ratio. So the signal to noise ratio is much higher for this chromatogram than for the other two for two reasons. Most of the spectral acquisition time is spent collecting just the data in a small range. This is akin to signal averaging because the detector spends much longer detecting that signal at 312, and very little other than the analyte of interest is generating a signal here at mass to charge ratio of 312. Now, even if we set the mass spectrometer to monitor a large range of masses, we can still generate what's called an extracted ion chromatogram. Here, the entire mass spectrum is recorded repeatedly during chromatography, and the one value of MZ is taken from each spectrum and plotted as a function of time. And we will observe a chromatogram similar to the selected ion chromatogram, but that selected ion chromatogram monitored just a single mass to charge ratio, or a small number of them, while the extracted ion chromatogram monitors the entire spectrum. And thus, the signal to noise ratio of the selected ion chromatogram will be higher. The extracted ion chromatogram is still useful to us, however, when we don't know what we're looking for. So we can still measure all of the masses and then just pick out those masses that it turns out we were looking for and generate a chromatogram with just those masses. So we can increase the selectivity and signal to noise ratio in a chromatogram using selected reaction monitoring, in which we use a triple quadrupole mass spectrometer. A mixture of ions is entering quadrupole 1 over here, and quadrupole 1 only allows selected precursor ions to pass through into our second stage, quadrupole 2. Quadrupole 2 passes ions of all masses to the third stage, Q3, but while the ions are traveling through stage Q2, then the precursor ions collide with nitrogen gas or argon gas at around 10 to the minus 5 to 10 to the minus 3 torr, and they break into fragments. And these fragments are the product ions that come out. And then Q3, our third quadrupole over here, allows only one selected mass to charge ratio to reach our detector. So we've got some precursor ions coming in. Q1 selects just the precursor ion that we're interested in. Those ions collide with some other gas molecules here, and then we have our product ions coming out. Q3 selects which product ion we're looking at, and those ions are the only ones that strike the detector then. So selected reaction monitoring is highly selective and can analyze at parts per trillion levels. So this is nanograms per liter. So let's turn now to proteins. We can use electrospray in studying proteins using mass spectrometry. Proteins typically have carboxylic acid and amine side chains, giving them a net charge depending upon the pH. An electrospray will eject these existing ions into the gas phase then. For example, the mass spectrum of the protein transferrin gives peaks corresponding to MHNN+, where N is some integer. And note that the peaks corresponding to ions containing more hydrogen ions are at lower mass to charge values because the charge is higher. Also note here that while the peak labels show the charges, so you've got MH36, 36+, and MH40, 40+, and so on, we don't initially know what these charges are. So to find the charges, let's consider a peak with mass to charge ratio of Mn, derived from the neutral molecule M plus N number of protons. So we've got M sub N has a mass to charge ratio of M plus N times 1.008 divided by N, and that gives us M over N plus 1.008. And we can solve this then for M over N, and that gives us M sub N minus 1.008. And the next peak at lower mass to charge ratio should have one more proton, so N plus 1, and a charge higher by 1, so again N plus 1. And that means that M sub N plus 1 is equal to M plus N plus 1 times 1.008 divided by N plus 1, which then gives us M over N plus 1 plus 1.008. And again, we can solve, and we get M over N plus 1 then is equal to M N plus 1 minus 1.008. And we can now use these two to get our ratio between N plus 1 and N. And solving that, we can then find n is equal to m n plus 1 minus 1.008 divided by m n minus m n plus 1. And we can then use any peak to find the mass of the neutral molecule. So m sub n minus 1.008 is equal to m divided by n, and thus m is equal to n times m sub n minus 1.008. And in this case, the mass of the neutral molecule happens to be 79,551.78. So proteomics is a branch of biochemistry in which the structure and function of proteins is studied. Mass spectrometry is used to deduce the sequence of amino acids in the protein. So first the protein is digested into smaller chains by enzymatic cleavage. Then the individual chains are then cleaved to make fragments of all possible lengths. And high-resolution mass spectrometry is then used to determine which amino acids are in each fragment. A computer is then used to reconstruct that sequence of amino acids in the original protein. And the polypeptides can be fragmented using electron-transfer dissociation. So an exothermic transfer of an electron from a gas phase anion to a gas phase polypeptide cation causes the peptide bond to break. For example, in this case, each of our 5 peptide bonds can break, and the charge could be on either the left fragment or the right fragment, and this gives us then a total of 10 possible ions. So you've got here bond 1, 2, 3, 4, 5, and that charge could be on either the left side or the right side after the bond gets broken. That gives us 10 possible ions. Note that where collisionally activated dissociation can cause other bonds to break in the peptide chain or side groups, the electron transfer dissociation does not. So that was chromatography-mass spectrometry.